Welcome to Embedded Systems for Spring 2022. This is one of the more fun courses, in my opinion. This is a course where you look at interfacing software and hardware. In your previous courses, like Circuits 1, you're kind of crippled. There's not much you can do without a microprocessor. Well, this course is kind of like the lab for the entire program. You've got circuits, electronics, interfacing the real world to microprocessor. You've got 173, C coding, as well as assembler, coding the microprocessor, and with that you can read the inputs, do some software, drive the outputs. With this class you can build roulette wheels, voting machines, stepper motor controllers, reflex timers, quite a few. It really opens up possibilities when you have a microprocessor. So that's this course. In this lecture we're going to go through the syllabus for ECE 111. Now, to start out, all the lecture notes are on a website called Bison Academy. If you go to Bison Academy, here's what it looks like. This has the various courses in electrical and computer engineering, bisonacademy.com. If you go under 376, that's this course. That takes you to the syllabus for 376. Now, what we'll be covering in this course is microprocessors and how to interface them to the real world and how to write code to control the outputs based upon the inputs. What we're going to start with is a little bit of background on microprocessors, the computer architecture, and Boolean math. We'll then look at a programming language called assembler. Assembler is machine code. It's how the processor actually runs. Machine code is what I call throwaway code. It's extremely fast, extremely powerful, extremely efficient, and insanely hard to read. But that's how processors work. So we'll talk about assembler, how the processor actually works, and look at some simple binary inputs and outputs, such as how to build a counter. Every time you hit a button, it counts by 1. How to make a light blink. I like saying that only engineers get excited when a light blinks. That means a lot. That means that your code compiled, it downloaded, your processor's running. That's a big deal. Once you get a light to blink, everything else is easy. We'll look at how to build counters, count how many times you hit a button, blink a light once per second, play a note so you can turn your pick into a one-key piano, play some talking head songs, drive LEDs, and NeoPixels are kind of a neat, pretty bright LED. This is kind of designed, or in this class, to lead into senior design. If you ever need a bright, colorful LED, NeoPixels are one way to do it. At that point, we'll have our first test. We'll then switch over to C coding. C is a lot nicer than assembler. With C, you have things like multiply, which is a big deal. You can divide. You have arrays. You have for loops, do loops. C really opens up the possibilities with what you can do with a microprocessor. 173 is a prerequisite for this course. If you don't really remember your C coding for 173, don't panic. The main things we need are addition, subtraction, if statements, for loops, do loops, subroutines. If you can handle that, you're in pretty good shape. Plus, there's a lot of sample code. I kind of like saying that I've only written one program my entire life. Over here, you've got sample code. This is something that runs. It's a way to start. It's a C program that'll, in this case, just turns on outputs the numbers 1, 2, 3, 4. It's a lot easier starting with the working code than modifying it to meet your needs. And this is kind of like your starter code for the various homework sets. So again, if you don't really remember your C code, don't panic. You should be okay. Once we get into C programming, we can do things like use an LCD display and display the current time. I can use a keypad and build an RPN calculator with your pickboard. I can drive stepper motors and have, like telerobotics, as you turn a potentiometer, the stepper motor turns with you. I can collect analog inputs, measure the voltage across the battery, measure the temperature in the room. Once I can do that, I can start collecting data and watch the temperature of a coffee cup as it decays, as it cools off. Watch the voltage across a capacitor as it drops off. Once I start collecting data, every time I collect the data, it'll be a little bit different. So to analyze randomness, that's where you need statistics. Statistics is actually a different course, ECE 341. But we'll do 3 or 4 lectures on statistics in here. This is really the lab that goes with 341. The problem with statistics is you need data to analyze. Well, in this class, I have a microprocessor. I can collect data. So we'll look at collecting data, like if I roll a die, can I tell if the die is fair? If I load the die, Can I detect that the die is loaded, or how loaded can I make the die and get away with it? I can do a t-test. Is my reaction time faster than your reaction time? Can I jump higher than you? That's a t-test. Then we'll have our second test. The next topic is probably the most confusing and most important part of this class, interrupts. Interrupts are really confusing. It's a subroutine called by hardware. So you've got a problem that you've got a code and somebody else is calling subroutines in your code. That's what makes it really confusing. It's really, really powerful. With interrupts, I can do things like keep track of time. I can set up the hardware so that it calls an interrupt every 10 milliseconds. By counting how many times I've interrupted, I know how much time has gone by. I can set up interrupts to happen every time you hit a button. So then rather than having to write the code that says, did you hit the button? Did you hit the button? Did you hit the button? I only call the subroutine when I need to, when I hit the button. It really simplifies some things, but it's a really strange concept, really powerful, really useful, and likewise, a third of the semester is spent on interrupts. We'll then look at filters. Anything I can do in software, I can do in hardware, and vice versa. In circuits 2 and signals and systems, you look at how to design filters with capacitors, inductors. Well, anything I can do in hardware, I can do in software. I can write a program to implement a filter. In hardware, you analyze the filter in the S-plane, where S means derivative. In software, you analyze it in the Z-plane. So the Z-transforms are something you're going to see when you get into signals and systems. We'll briefly introduce it here, because this is kind of where you actually apply it. If I have a microprocessor, I can implement a filter, but to analyze it, I really need to use Z-transforms. Then we'll have our third test. So that's kind of the outline of the course. The different websites. There is no textbook for this class. The textbook, well, actually, there is kind of a textbook. The textbook, if you go under Resources, is the PIC 18F 4620 datasheets. It's about 500 pages of instructions on how to use the PIC processor. These are accurate. That's the nice thing about Microchip. They actually have accurate data sheets, which isn't true of all companies. So if you want to do something like look at how to use the different registers, here's an explanation of it. Somewhere in here, here we go. Here's a list of the assembler commands, how they operate. This is actually the textbook for the course. A little bit hard to read. The other textbook for the course is here on Bison Academy. Here I kind of go through the data sheets and explain the different parts piece by piece. So under here, like let's go under inputs and counters. I've got the lecture notes in portrait format. That's nice if you want to print them out. They're also in landscape format. Landscape works a little bit better for videos. So the videos that I've recorded in the class presentations will use the landscape format. They should be the same. You've also got the recorded lectures. If you are taking the class online, you're welcome to watch the videos. You can attend the class in person, or you can also just live stream the class. Class is at 1 p.m. Monday, Wednesday, Friday. I'll send out the Zoom link shortly. It'll also be posted on Blackboard if you'd like to live stream the class. Otherwise, everything we cover in class is covered in the videos. You've got sample code. In the lectures, typically there's some coding in here. This is the same code, so you don't have to dig through it. This is also the starter code. Like I mentioned before, it's a lot easier modifying code that works than starting from scratch. So for the homework, typically this is some starter code you can use to attempt the homework. And then the homework assignment. So each week there'll be a homework assignment. Do the following week. There's also a lab part. That's where you start testing your code on your PIC board. So that's under Syllabus. The PIC board I'll talk about in just a sec. Under videos, there's also a YouTube playlist. If you'd like to binge watch and watch the entire course over one night, here's your chance. Under homework sets and solutions, this course has been taught for quite a while. These are the homework sets and solutions from previous semesters. I've cleaned up the code, the solutions a little bit. I've taken out most of the actual coding, so you just can't copy the code from previous semester, submit it this semester. You got to write the code yourself. But this is a good place to go if you want to see other samples of coding, other sample problems, the solutions, minus the coding, for quite a bit of it. Under Best of 376, this is kind of a fun spot. On quite a few of the homework sets, I'm going to ask you to demonstrate your homework. One way to demonstrate it is to demonstrate it in person. Another is during office hours, you can demonstrate it over Zoom. Another way is to make a YouTube video and just send me the YouTube link. That's what these are. People that made a YouTube video of their homework problem and give me permission to share them. So here's what you can see what other students have done with embedded systems. Kind of fun to go through. And under resources, again, the data sheets for the PIC processor. To get your PIC board to work, you're going to need a MPLAB 8.92. You can get that from Microchip. There's also a link here. When we get to C coding, you need a C compiler. That's this link. That's much we have under resources. So that's what Bison Academy has. So let's start with the syllabus, the first lecture. Now, I'm Jake Lauer, of course. This is ECE 376. Class meets Monday, Wednesday, Friday at 1 p.m. in Ag Hill 326. You're welcome to take the class in person in Ag Hill 326. The class will be live streamed on Zoom, or you can just watch the YouTube videos online, or mix and match wherever you like. The lab times, this is an open lab. Everybody will have a lab kit, so you can program your board at home in your dorm room, wherever you like. There's also room 211 and 237, I believe, have computers that you can use to program your boards, as well as the computer cluster, if it's done. My office hours are Monday, Wednesday, Friday, 8 to 10 a.m. I'm usually around most of the day, so anytime I'm around, you're free to grab me. And the textbook is really Bison Academy. The prereq for this course is 173 C programming, 275 digital systems, AND gates, OR gates, Carnot maps, and 206 circuits 1. If you're a little bit fuzzy on some of those, don't worry too much. We kind of explain what you need in this class, but you should at least have seen what is C programming, what is a subroutine, what is an if statement. If you're not really real keen on what those are, at least they're familiar terms with you. By the end of the semester, you should be very familiar with if statements, for loops, subroutines. The course objectives. By the end of the semester, you should be able to solder a circuit board. We used to have students graduating who never soldered the entire time that they were here at NDSU, and that just doesn't seem right. So in this class, part of it is you're going to have a kit that you get to solder, so that at least you've soldered once before you graduate. Second advantage is that this course is a lot more fun if you can see your programs actually working in action. That's what your circuit board does for you. It lets you write code, download it, and test it, and demonstrate it. You should be able to interface your microcontroller to binary inputs and outputs, such as read a push button. Every time I push a button, turn on a light. After 10 button pushes, I turn on a motor. You should be able to interface your microcontroller to analog inputs and outputs. I should be able to read temperature, say 0 to 50 degrees Celsius. I should be able to vary the brightness of an LED from 0 to 100% brightness. You should be able to control the inputs and outputs using programs written in assembler and C code. Assembler is going to be kind of limited. Assembler is really hard to use, so it's really just binary, kind of get a light to blink, kind of build a counter. When we get to C coding, C really opens up the possibilities. That's why we use C so much in industry. With C code, you can build a roulette wheel in about 20 minutes. It'll be really hard in assembler. And you should be able to use interrupts to control the precise timing of a microcontroller with precisions all the way up to 100 nanoseconds, which is really amazing. With the processor we're using in this class, I can measure time to 100 nanoseconds. 100 nanoseconds is the distance light travels 100 feet in 100 seconds. I can almost measure the speed of light. Relativity almost comes into play at 100 nanoseconds. If you hop on an airplane, fly to London and back, time slows down by 15 nanoseconds. You can almost see relativity at these speeds. So Time is something you can measure insanely accurate with a microprocessor. Even with this processor we're using in this class, a fairly simple one, you can measure time insanely accurately. So that's the objectives. We talked about this a little bit beforehand. The lecture notes, everything for this course is on a website called Bison Academy. There you've got the syllabus with each day's lectures, videos of the day's lecture, sample code, homework, and once the homework's turned in, I'll also post solutions. Under homework sets and solutions, you've got the homework sets from previous semesters along with their solutions, and occasionally a YouTube video. This is typically for like fall 21. That was one of the first semesters where we had online and in-person instruction. The videos are for online students. If they wanted to watch, we go through the homework set, here's a YouTube video of it. And if you want, you can also rewatch that video, relive the glory. Best embedded systems, again, kind of a fun page where you can see what other students did in the past for their various projects. It's also a good recruiting tool for ECE. We kind of show this to high school students as they come around. And a comment we've gotten from companies. Everybody kind of looks alike on paper. To help differentiate you from everyone else that's applying for a job, if you would make YouTube videos of your better projects in your classes, you could post the links to those videos on your resume. Companies will look at those. It helps differentiate you from everyone else. Also, during job interviews, I used to work at Fisher Controls, and when you interview at universities, it's really mind-numbing. After 3 days asking the same questions 20, 30 times a day, you kind of go into a coma. If somebody comes in and gives you something different to look at, such as, here's something that I did in my class, that's something you're going to remember. It really highlights your day during job interviews. You've got something you can actually see. Plus, from your standpoint as a student, you can direct the interview towards something that you're very familiar with. This is your project, you know what it is. So I highly recommend making videos of your projects. Lab kit. I mentioned this a little bit before. In this class, everybody is required to have a lab kit. These are $65 from SWE. If you have a previously built lab kit from the previous semester, that doesn't count. Part of the objective is everybody should solder once before they graduate. So you need to get a new lab kit, so you solder at least once. The lab kits are $65 from the Society of Women Engineers. Checker Cash works. It's actually about $100 in parts, but in the summer we buy them in bulk, paid by SWE, and they pass the discount on to you, and use it as a little bit of a moneymaker. You can pick up the lab kits in my office, ECE 201, throughout the week. What the lab kit does is it allows you to test your code in hardware. The course is a whole lot more fun if you can write your code, download it, and see it working. Also, you'll learn by doing. About the only way to understand the concept in this course, especially interrupts, is to actually write a program that uses interrupts and see how it actually works. It also helps with debugging. It's really hard to spot bugs in your code. If you watch it run and you notice that, hey, these buttons aren't working, then you know which part of the code is at fault. Why aren't these buttons working? Where's the section of code that controls those buttons? Also, this is a lot like weightlifting. If you watch somebody else lift weights, you don't really get any benefit. You got to do it yourself. These boards let you do it yourself. They let you write the code and test your code and debug it to see that it works. With the boards, this is probably the first time you've soldered. If you need help soldering, I'm more than happy to help you solder, help show you how to solder. It's not too hard. It's tedious, but not too hard. I can show you how to get started, and you'll probably do a pretty good job at soldering. If you have a complete disaster on your circuit board, don't panic. If your board quits working halfway through the semester, don't panic. Usually it's just a bad solder connection that I can fix within 10 or 20 minutes. I also have a bunch of spare boards, so that if your board quits working, I'll just swap out a board with you, so that you have a working board. You need working boards to do the homework, and then I can fix your board. Then when somebody else comes in, I'll swap boards with them too. The course is a whole lot more fun if your board works, and it also helps with completing your homework assignments. And does affect your grade. It's hard to demonstrate a working board with a non-working board. For taking the course. This course you can take any way you like. It's offered 3 ways. You can take the course in person. There's plenty of room in the classroom. All students are welcome to attend the class at the designated class time and location. Note, however, that face masks are required if you're showing up in person. I'm going to be wearing them. Everybody else should wear them. You can take the class via live stream. All classes will be streamed on Zoom. I'll share the Blackboard link. Share the link on Blackboard probably Friday or Monday coming up. If you want to feel like you're participating, you can wear a mask while you're live streaming as well. You can also watch the class online. All lectures have been recorded and placed on YouTube. And you can also change your mind on a daily basis. If it's a really, really cool day, you can live stream it or watch it on YouTube. If the next day is kind of nice, show up in person, your pick. With that being said, one slight caveat, in-person does appear to be better than online. Fall semester, fall 2021, was one of the first semesters where we had this class in person and online. So it's one of the first times to actually have data to see how the 2 classes behaved and performed. The course evaluations. Course evaluations were almost a letter grade higher for the people that took the class in person. So people enjoyed the class more when they took it in person. They got more out of it. The overall scores. The people that took the class in person did about 7%, almost a letter grade better than the people that took it online. That's not to say that if you take the class online, you can't get an A. Plenty of people that took it online got A's. But just for full disclosure, in-person does appear to be better than online. This isn't really definitive proof. It's a sample size of 1. There could be a sampling bias. But given a choice, I think in-person is better than online. But again, there may be other factors involved in your decision. However you want to take the class, it's your choice. And again, you can change on a daily basis. In terms of grading, this class is going to have 3 midterms, homework, term project, and a final exam, all with equal weightings. So the average of all those together is your overall average. Your overall grade, if you have a 90% or higher, guaranteed you have an A. 80% or higher, guaranteed you have a B. I'll curve down, but I won't curve up, meaning 90% guaranteed is an A. 89%, it depends upon the curve. Typically, 89 is right about the cutoff between an A and a B. So usually 89 is an A. It depends upon the curve. I do that so that if you work together in a group and everybody learns the material, everybody gets a 90%, I'm happy to give out all A's. I'll have to justify it to my chairman, but if I can demonstrate that people learned how to do binary inputs and outputs, analog inputs and outputs, assembler coding, C coding, you understood interrupts, that's justification from my standpoint to give everyone an A. To get an A or an B, do the homework. Again, this is like weightlifting. If you watch somebody lift weights, you're actually not getting the benefit. You got to do it yourself. Same thing with programming. You got to write the programs, you got to debug them, you got to go through the hassle of trying to figure out why it doesn't work. The only way you know how to program, to learn how to program, is you got to do it. That's the purpose of the tests. On the homework, you've got the whole week to do the homework, you've got the internet, you've got sample code. I can't really tell, are you doing the homework yourself, or are you just giving moral support to somebody else who is doing the homework? That's why we have the tests. The tests are really to test, did you do the homework, or are you giving moral support? If you do the homework yourself, you should get an A or an B without much problem. If you're giving moral support and you get to the test, you're going to really struggle on the tests. That's kind of the purpose of the tests. So typically this class is a bimodal distribution. One group that's getting A's and B's, another group that's getting C's and D's and F's. That's my guess is the people that do the homework and the ones that are kind of sliding by during the week and then get hit with the midterms. So do the homework. For the homework and lab projects, you're allowed to use groups of 1 or 2. The reason I don't do 3 is typically when you have 3 people in a group, one person is giving moral support. So do the homework, work in groups of 1 or 2. If you do work in a group, you only need to turn in 1 homework per group. Just let me know who else is in the group so everybody gets credit for it. And again, the exams serve to check to make sure that you actually did the homework, that you understand the material. So if you divide up the homework, one person does the hardware, one person does the software, make sure you understand both because both are going to be on the exam. Also, the homework is kind of open-ended. This kind of bothers some students. On most homework assignments, you're free to do whatever you want, providing you do something like use C coding, use the stepper motor, use the analog input, include timing. That lets you tailor the homework based upon your own interests. Also, some feedback we got from industry. The typical homework assignment where you do some analysis is a very small part of the engineering design cycle. The whole cycle includes requirements capture, hardware design, software design, testing, validation, and demonstration. So the homework kind of walks you through all three of those as well, or all four of those. Typically on the homework, since each one's different, you've got to tell me, what are you doing? Are you building a roulette wheel? Are you building a reflex timer? Are you building a flashlight? What are the inputs? What are the outputs? What's it do? You then have the hardware design and software design. What are the hardware connections to your PIC board? What's the software to control it to make it do what you want? You've got testing. How do you know that the hardware is working? You'll collect some data at the lab to make sure that the push buttons work, the LEDs are working, I'm outputting 1 kilohertz. And validation goes back to the requirements. If the requirements are, I want to generate 3 frequencies, 3 notes, 120 hertz, 220 hertz, 320 hertz, validation is going to the lab and measure. Did you produce 120 hertz, 220 hertz, 320 hertz? And then the demonstration is demonstrate to me that your project or homework actually does work. That can be in person or YouTube video. And some legal stuff. Attendance is required. Again, in this class, it's your pick. In person, live stream, YouTube videos. If you have special needs, we'll accommodate them some way. Let us know and we'll do something to accommodate you. Academic honesty. The material in this class, this is a required course to graduate for a reason. You're going to need this stuff, need this knowledge when you graduate. Our graduates build defibrillators, pacemakers, flight controllers. That's all embedded systems. C code, assembler code to control the outputs based upon the inputs. If you can somehow get through this course without learning anything and getting an A, that's not going to help you when you graduate. The whole reason we have this class is you're going to need this information. The goal of academic honesty is do your own work. Again, you're going to need this knowledge when you graduate. It's better to learn it here in college than on the job. So if you can figure out a way to get through this course and get an A without learning anything, don't. Again, that's not really the purpose of the class. And if you're a veteran or a soldier, again, if you have problems with the midterms or attending class, let me know. We'll work out something. So that's the class. It's, again, in my opinion, one of the more fun classes in the program, one I really enjoy. It's basically the lab for the entire ECE program. And with that, we'll let you go. I hope you enjoy the course. Again, I enjoy teaching this course and hope you enjoy it as well.